times that gives me that. It's this times that gives me, so is 0. It's the same correspondence, like that mess of letters with numbers, and I like took that system of equations and I rewrote it as a matrix problem. That correspondence between equation and matrix version of equation is that correspondence I'm using. So it's the matrix column multiplication. There are problems in the book to help you guys get up to speed on that. I may even not even assign them like specifically. I don't always put those in the homework because if you need more background on that, you go seek help. There is a section in the book, I want to say like 9.1 or 9.2. There's a couple sections in the book in chapter 9, I think, that actually have the basic matrix calculation stuff in there. So.
And you have a series of section lecture notes that just deal with the calculus and algebra involved in this?
No, I don't think I have any. I don't have much in the notes on this, but there's the section in the textbook, and I also have solutions to those from when I started teaching this. I've written, they're posted there. Beyond that, if you have questions, just send me an email. I can point you to more resources. But keep asking questions. It's good. It's very good. So anyway, we've found eigenvector for eigenvalue 1, our eigenvector for eigenvalue 3. Now I put it together. The general solution is x is equal to c1 e to the t times eigenvector 1 minus 1 from my first eigenvalue plus c2 e to the 3t 1, 1. And there you go. This is the vector form of the solution. That's how you solve these. Now I can unwrap this. Let me go back to x and y. So what is this? What are actually x and y here? So this means x is actually equal to c1 e to the t plus c2 e to the 3t, right? And y is equal to minus c1 e to the t plus c2 e to the 3t. So this is what I would call the scalar solutions. This is the vector solution. I don't usually want you to find scalar solutions, but I'd like you to know how. I mean, you should know how to find the scalar solutions if you want to, but at the same time, I'm fine with you guys communicating your solution to me as a vector solution because it's easier for me to see what you did. And if you can find the vector solution, you can find the scalar solutions. It's just a matter of figuring out components. It's not a big deal. Does this make sense? So you notice this is nice because now we have a method. We don't have to somehow, see, to do the method of example 1 on this example, it's a mess. See, because there's x and y in both equations, right? So if you tried to do what we did in example 1, and you tried to somehow solve for one in terms of the other, it requires some kind of sneaky steps, right? I mean, they're coupled. But the thing is beautiful about this eigenvector idea is it automatically uncouples them somehow through linear algebra, and then we are able to just build solutions without ever actually having to do any kind of elimination. We have a straightforward method. We find the characteristic values, we find the eigenvectors corresponding to those characteristic eigenvalues, and we build the solution. And that's it. Until it doesn't work. For example, my example 1 would be troublesome in our current technology. Right? This gives us what? This gives us matrix 0, minus 1, 1, 0, right? So what's my characteristic equation? Uh-oh, this has lambda equals to plus or minus I. So my example 1 has pure imaginary eigenvalues. So we'll talk about what to do with those next class. All right, those are, you can find a complex eigenvector. It gives you a complex solution to the differential equation. The real and imaginary parts of that complex solution are separately real solutions. And those are the ones we derived with this ad hoc method today. So, now, fear not. You might have worried that I was actually going to calculate the characteristic equation for this. Have you guys been doing that? Did you work it out? Is it nice? No? Yeah, I'm kind of scared. I mean, we could try to set it up. Here, I will foolishly attempt. I'll at least write it down. What's the characteristic equation? I'm not going to actually calculate it, but so we'd have minus lambda, 1, 0, 0, 0, minus 3 minus lambda, 0, 3, 0, 0, minus lambda, 1, minus 2, 0, 0, 1 minus lambda. So the way this works, just put some dividers in there, is, this is the determinant of A minus lambda I. So all that does is it subtracts lambdas from the diagonal. Otherwise, it's just the matrix A. So setting up the characteristic equation, we just have to subtract. But then you've got the determinant of a 4 by 4, which I just don't feel like doing right now. I mean, you could do it, but that's probably not a good idea. I mean, I don't know. There's another way. Let me show you that way. Now, of course, you guys know the MATLAB, right? I think you guys are introduced to MATLAB pretty early on, right? You guys know about MATLAB before you know about linear algebra, am I right? And I think you guys solve systems of equations before you've had 221 too, right? You guys solve systems of equations in your introductory circuits course. I've heard the Calc 3 folks talking about that. They're from before your time. So you electrical folks in here have already had, but I guess not everybody's electrical, huh? So some of you are in less awesome engineering. Oh, I'm sorry, no, wait, no. Just kidding. I was once upon a time an electrical engineering major, so I still harbor a certain amount of arrogance residually. Mostly kidding. Come on. So you guys know my website, I think. Can you get the lights, King? Thanks. Oh, now I need my laser. Now, I definitely do have more examples of the eigenvalue problems in my notes. That I didn't, but anyway, so my website, supermath.info, and eventually I have this links to websites to do the math for you. This third one is actually a great way to calculate reduced row echelon form of a matrix if you want exact fractions. It'll even show you the row reductions. So if you want to learn how to do row reduction, step by step, carefully, this will actually tutor you in that. Here, I'll show you. Go reduced row echelon form matrix. Suppose I wanted to solve this system of 3 equations, and I'll make it a non-homogeneous problem. Ooh. Yeah, I don't know. You pick some numbers for me. There we go. So it actually tells you the row operations and step by step, and check it out. Yeah, so the solution is x equals minus 33 over 10, y equals minus 157 over 10, and z equals 159 over 10. The system of equations I started with was 3x plus 5y plus 6z equals to 7, 8x plus 3y plus 5z equals to 6, 5x plus 3y plus 4z equals to 0. So this is available. Just kind of awesome. Of course, you know, if you just look for, this would be a solution for that equal to 0, what do you think we're going to get? We're going to get 0 is the only solution, right? So same math, but we get 0 in the last column. All right, anyway, I digress. So there's that website, which is pretty awesome. Not so much relevant to this course. More relevant to you guys, eigenvector calculator, ugly numbers, no problem. Number 4. This is where it's at. I prefer the old version of this calculator for various reasons of Java and such. Here, we just looked at the matrix 1, 2, 2, 1. Calculate eigenvectors and vector eigenvectors. So there you go. Characteristic polynomial, x squared minus 2x minus 3. And the eigenvalues were minus, wait a minute. What? Oh, did I do the wrong matrix? What was my matrix? Oh, I was like, you guys would have corrected me, right? So it was 2, 1, 1, 2? All right, that's better. Although that other one's a nice example. So there you go. Check it out. These are in fact, it even made the same choice of eigenvectors as I did. But you could do other things, like you could norm the eigenvectors to have length 1. There, check it out. Now, what's that done? This is what your Texas Instrument calculator usually does. If it calculates eigenvectors for you, by default, it normalizes them to length 1. All right, for reasons I'll maybe talk about another day. Now, let's see here. So you guys are going to have to help me because I can't read that matrix over there. What's my, can you turn the lights on? What's my example? Can you read me row 1? Yeah. Zero, minus 3, 0, 3. Okay. 0, 0, 0, 1. Negative 2, 0, 0, 1. Right. And I like to not do that. I like to have what I have first coordinate. I don't want that either. I want integer if possible, I guess. I don't know. There. Well, anyway, it's unpleasant. Yes, so I stand by my conviction that I shouldn't actually work that out in detail. The solution to this, so did you guys do it by substitution? Did you do it by substitution earlier? No. If you had, you would have found a pair of sines and cosines for the 1 and then exponentials. So it's got sines and cosines and exponentials in it. Yeah, that one's quite awful. But this much I can tell you, one solution to it is e to the minus 3.4 t times this vector. That is one of the solutions to that system. Another solution to it is e to the 0t times this vector. In other words, that means that x3 equals to a constant is a solution to that system. Can you see that? x3, if y is equal to a constant, it solves this. Do you see that being true? But what about that 2x? How's that work? Well, anyway, I'm overlooking something here as I interpret it. Well, anyway, don't mind me. We're out of time, so. Anyway, sorry they don't have your test back yet. I hope they have it back next time. We will continue. I'll try to work some more examples, and we'll be on to complex eigenvectors. And there we go.